to restart, we want to reaffirm our values, and especially during the discussions, let's remind ourselves to be kind, to be trustworthy, respect, we believe in diversity, we believe in inclusiveness. So let's just take 10 seconds, just to remind all of us all the values we strongly believe into. Okay, so here is the schedule for today. So we are here. I think you can see my cursor. We're gonna start right now with a few summaries from the findings of yesterday's discussions. I would do maybe first the in-person. You can come up here at the podium, and later we do remote.
Okay, so good morning, everybody. Good afternoon for the other from Europe, Asia, Africa, and Oceania. Just a few minutes in order to report what happened yesterday, and then we will talk about what we want to do today. So yesterday, at the end of the day, from the in-person people, we decided mostly to start from the paper of Igor et al. 2022 and take the observing scenario of 05. So we can take the nominal and also the pessimistic scenario as a reference. So in order to, and we have to, of course, update the coverage. So we decide to go for each event. So neutron star, neutron star, neutron star, black hole, black hole, black hole, merger, and gravitational wave lensing. And we will, at the beginning, I think we decide to have a discussion all together about the rate, together with Shreya, that can help us to talk about this. And then we can decide if we want to split for each event in order to do number, we have to be quantitative, of course, today. So what we made yesterday from our discussion was that, we have to see, of course, if this event is visible from Rubin, or what time, which exposure time we have to achieve for a particular magnitude, how many tiles we need, how much time per trigger, per filter, per epoch, and then we can, together with the calculation of the rate, we have to think about all the quantities that we want to report to the SCOC. So depth, time frame relative to trigger, area, and bands. So we talk also about for the BH science, because it's a little bit different between respect to neutron star, and neutron star black hole. Yesterday, we understand that we would need to focus only on the most well-localized events, given the number of potentially associated flares, and also that we need to revisit, of course, several times as the other events in order to constrain the cavity model, if I understand correctly. So, of course, we must stay inside the budget of the 3%, of course, so we have to repeat this because we have to calculate the number of visits in order to stay in the budget. And then we have also some discussion about gamma ray bursts and fast radio bursts, but maybe this is to talk a little bit better today, because we have to decide if we want to take this kind of events inside this budget, or take into account other things. Then there was also some discussion about the unexpected sources. So for the unscheduled target of opportunity, which is part of our baseline, but maybe for this also is not to take into account inside the budget, because we have to maybe have clear guideline for how to execute them. So this is most our summary, and I give the floor to Stephen. Yeah, it's okay. Stephen, if you are online, you can give us your report of today.
Yes, can you hear me okay? Can I share my screen? So we had a really useful discussion online. There's about 10 of us. I put in the notes here into the document. So this is what we thought. We discussed the GRBs as well. We thought really there's no clear viable strategy for GRBs as a whole. It's possible you could hold out for the most luminous events like the boat or 230307A if there was no counterpart the first day or so, but the number of poorly localized GRBs is too large for us to cover them all. So then what would the strategy be? What would the filter be? And the only thing we could think of is luminosity. Like you take the rarest, highest, the brightest GRB of the last 5 years or something and maybe do that. That's the only way we thought it was possible. We picked up on Tiago's idea. So for the GRBs, that was our thought. The GRBs, I don't really see there's a viable strategy there. Then we thought, what about the binary neutron stars that aren't well localized? We picked up on Tiago's idea of shifting the wide, fast, deep strategy. So if it's 1,000 square degrees, it happens to be a really high signal to noise binary neutron star. It's 1,000 square degrees because only one detector was on. Could you just shift the wide, fast, deep strategy and just do that? Just do normal wide, fast, deep, but do it in that region. So we thought that was really interesting. And a way to bridge the gap between really the events that I think you referred to in the text here as gold, but just happen to have only one detector. And so as we were thinking of that, we thought we didn't like the use of gold and silver. We thought it might be confusing because you can have gold events which are very poorly localized. 190425 is an example. Really high signal to noise event in one detector. Only one detector was on, so it was 4,000 square degrees or so. It's probably better to class these by small, medium, and large map sizes. So the small are down at below 100 square degrees. The medium, a few hundred, and large is up at 1,000. I have different strategies there. We thought that was a better split and a better way of describing them. And then we're going to need soft boundaries. So it doesn't make sense to have it's under 100 square degrees, do this. If it's 140 square degrees and it's a high signal to noise event, you would probably do the strategy for 100 square degrees. We discussed the baseline expected numbers for binary neutron stars. These are in the slides. I've posted them in here. Bottom line is, whatever way you do this calculation, even starting from the current binary neutron star rate, the rough projected number we're going to get in 05 is somewhere around 10, plus or minus 10, probably. And so with that, you can do it in different ways, but those numbers aren't likely far away. Which means if you took the Andreoni strategy, 6 hours per trigger, you're looking at around 60 hours over the 2 years of 05. So again, we can discuss all of this, but this is what we thought was baseline and reasonable. We like the Andreoni strategy, of course, particularly the roughly 6 hours spent on 100 square degrees event. The 3 shots in Andreoni paper, the 3 shots per night, followed by night 2, we thought that was good. But we're going to have to be really careful with SkyMap observability. If you can't observe for 4 hours, but you still need to do 2 passes on the SkyMap because you need to remove the asteroids. So we're going to have some flexibility for the observation window for the SkyMap. We need to do the same baseline numbers here for the neutron star black holes, but a useful discussion there. I mean, Mikhail thought only really 10% of these have the ability to disrupt, and the other 90% might not be visible at all. So we can't really do on the fly strategy. So we will need a careful decision process for the NSBHs. That was probably the most uncertain thing for us. And then, of course, we flagged up the issue. We really need to we have all Sky templates ready for the start of 05 for differencing. But from Eric, yes, comments yesterday, that's probably okay. Thanks. But it was a really useful discussion in the small.
Yeah, we have some comments from the room. First, from Fed.
Hello, this is Federica Bianco. So this sounds terrific, and I see already a lot of progress. It's very exciting because there wasn't a lot of time to work on this yesterday, so this is great. It seems to me like right now we have essentially like a multidimensional space to see the potential of a particular transient, a particular trigger, and evaluate whether or not it should be followed. I hope you can come up with like a way to combine. I like the idea of the soft boundaries around the area, weighted by the confidence of the trigger and all of that. At some point, this has to converge onto like a single score, right? So that we can put it in an algorithm. And that would be a really great approach, because if we have this score, then that diffuses the problem a little bit of the fact that we don't know the rates, because if the rates change, we just need to change the threshold on the score, higher or lower, to use the time wisely and not run out of time at the beginning of the program, or not underutilize the program. So I think if you can come up with that, that'd be great.
Yes, I think too. There. Oh, sorry.
I have a quick question for the project. I'm not sure who's, oh, sorry, my name is Adam Miller. I have a quick question for the project. So if the standard mode was to be 30-second single snaps, my understanding was that part of the reason for doing 2 15-second snaps was to help with asteroid rejection. So cosmic rays, sorry, never mind. I retract my question.
This is David Sand, University of Arizona. I'm wondering if we've considered, I'm sorry if this has already been brought up, for these large maps at high signal noise, whether we would just tile the highest probability regions for some of these rather than going for the full 90%. So several events that have large areas, just tile the highest regions, maybe at the soft boundary of 140 square degrees.
Yes. Igor?
It's Igor Andreoni, and I think, like, for example, in ZTF, we have a threshold. There is more like at least 70% of the area to be imaged for an event to become viable. I think this has never been considered, like in our discussions within for Rubin, and absolutely should make it to the final findings, in my opinion. So thank you for bringing it up.
Any other comments on the GWK's report? If
Yeah.
not, I propose. Yes,
yeah.
we do.
Can I just
Okay,
say
let's-
something on that last comment? I mean, Tiago's idea that has just come out. That's really interesting. I think we should develop that over the next few days. So what David said and Igor said there is correct. But this is just something new that's being floated, and I think for all of us it's quite interesting. But we should develop that a bit more in some more detail.
Agreed. Yep.
Yeah, one thing just on the soft boundaries and stuff, I think Bob, in Bob's initial presentation, I think he sketched out an idea of how we would make decisions, and that you have a committee and then there would be a Rubin observer as well. So although Fed says an algorithm, which I think we do have to do, I'm encouraged by this idea of having, real decision-making process during the night, have people on call. It's got to be down to us at some level to make the call and then push it to the observatory. But I think having people in the loop and who are on a rota and on call and ready to react and make a decision after the algorithm does its thing, there will always need to be some decision making there. But I think from the way Bob sketched it out, I think that would work.
This is Federica again. Yes, this is exactly the direction in which we're going, to have an algorithmic decision that is automated and to have supervision over that decision by an observer at the observatory that can override the decision either way, choose to pursue something that was below threshold, or not to pursue something that was above threshold, or interrupt the observation with the support of the community advisory committee that will be set up.
Thanks. This is Jeff Cookie. Just quickly, I like the ideas that are going around. I was just wondering if it'll consider, or how do you consider when the sky map changes? How does that change the ranking and score and decision making? So like say a day later, it's significantly different.
Yeah, that's something that we have to consider. If the sky map changes, what do we want to do? And that's something that the algorithm needs to be able to handle, I believe. Yeah.
Then, right? Sorry, but that can be as much as cancel, right?
It can be.
Yeah.
It can be. Yeah. It can be. Yeah. And as a community, we can say we really appreciate the idea of having a human there that does the last vetting. I think it's amazing, and thank you for enabling that. Okay, so we are, yeah, I think it would be wise to move on to the neutrino science case. So. Thank you.
Right, I will be brief. So yeah, we met yesterday. We discussed the two main science cases, so galactic supernova and TeV neutrinos. So maybe I just go through quickly the galactic supernova first. So I think the main take-home message is that this is maybe the only one that we have in our scientific lifetime if one hits. So we should absolutely trigger on any compelling event. And Rubin has a lot of different capabilities, and realistically, we can come up with a good plan to start off, but we should expect that this should be modified as a counterpart is identified, as the light curve changes, etc. So what we really want is to have a plan for the first few hours, and then we should sort of take it from there. So in general, the discussion was that there should be almost certainly a snooze alert, the supernova neutrino early warning system alert, and then there would also be a localization from either Super K or its successor Hyper K, which is scheduled for 2027, so very much in Rubin's scope. And we're sort of still aware that the landscape may be changing. There's new neutrino observatories coming online as well, but at least if there's one of these, there should be a localization that Rubin can tile. If we can tile it, obviously there can be a lot of extinction, so safer to go for a red band, for example, I band, at least at the beginning. Once you found a counterpart, you can then transition to trying to maybe get the extincted blue emission. So for example, we would expect U-band to be really useful here because maybe Rubin is the only thing that could detect the extincted U-band from a galactic supernova if it was very low latitude. And yeah, I think that's most of the information there. I mean, the other things, of course, not only do we want to find a counterpart, there's shock breakout, and then there's the light curve, right? So as soon as possible is obviously very much what we're interested in, and depending on the specifics of the supernova, there can be a delay between the neutrinos and the light from the shock breakout, and we won't necessarily know how much this is in advance. So that's also something we have to just be open-minded about, that we might have to tile, and then something will appear later. And then on the TeV neutrinos, our strategy here was sort of initially based on ZTF, and then obviously taking advantage of Rubin's different capabilities, in particular its depth and multiple colors. So I think similarly to ZTF, we have a range of different science cases we can target. We want our follow-up program to do all of these, but cheaply. So what we thought is to do one very deep exposure as soon as possible, day 0, in G-band for like a baseline to constrain rising sources, potentially fading sources, and then a second one in R and in Z to measure color. And then on the next day to just do G and R, and then on day 7 to do R and Z again. And then that would basically be able to detect rising sources, fading sources, sources that are very red or very blue, and sources that change color dramatically. And if we do this, it's 450 seconds for one neutrino, because we don't need to trigger on ones we could cover with one pointing. So that's 7.5 minutes per neutrino. There are maybe 4 good triggers a year at the moment. So that's, you can do the math, not an enormous amount of time. It's 30 minutes a year. There will be more neutrino observatories coming online, and we propose to just be consistent in our criteria, which is that it's highly likely to be astrophysical, so more than 50%, and can be covered well by a single Rubin tiling. So as new observatories come online, our ask may increase, but you know, if there's another one, maybe it goes up from 4 to 8 a year or 12 a year. It's still not an enormous amount of time. It's 90 minutes a year, so should be cheap. And yeah, I think that's pretty much it. So are there questions?
Yeah, we have ample time for the discussion. Daniel, Adam, thank you. And just a reminder, please
Hi, this
introduce
is
yourself. Yeah.
Adam Miller. Just a quick note, if you're doing sort of a single long exposure, I would encourage you to consider possibly multiple exposures where you dither so that you can cover chip gaps. And you'll lose, some area if you're just staring at one spot for a long fixed amount of time. And and then to be sure I understood, you're saying for the TeV neutrinos only triggers if the localization area is less than 10-ish square degrees?
So what I had down was maybe 6 or 7. The aim would be to cover 70% with one Rubin tiling. So
Okay.
that would be our official criteria.
Thank you.
Are there comments from people online? Thoughts?
Maybe just, this is Federica Bianco, I'm gonna take the opportunity just a second to remind everybody for all the science cases that the filter changes do take some time. They take 2 minutes. And so consider this also when you think about your time budget. I'm still encouraging to just having back of the envelope calculation for how much time a program can take. Then we'll simulate it. We'll know exactly how much it takes. And more importantly, what is the impact on the wide, fast, deep, and the other science programs. But keep in mind that in addition to the number of visits, like one filter change costs you 4 visits, roughly speaking.
Hello,
Yes, please go ahead.
Tony here. Just a brief comment regarding tiling. I think something like a hexagonal close pack or array, like think of bees. They figured it out before. Will have slightly overlapping everywhere, so we don't have to have a chip gap issue. And so that I think is much more effective. And if it's 30-second or 15-second exposures, it can be reused for the main survey. The other comment I'd like to make is that the ordinary transients that we have to detect and then retire as candidates, there are two types of them. There's of course, continuous asteroids, and the other is quasars. They're popping off unannounced, coming up above our 5 sigma threshold continuously as a function of time. Thanks.
So I just wanted to add that if you're looking, Peter Nugent here at Berkeley, if you just wanted to add, if you're looking at supernova in our galaxy, you're going to go through lots of extinction in general, right? So the redder filters are going to get you mostly what you want. However, the star situation is going to be unfathomable. Okay. And so I think you need to work this out, but lots of short exposures that you're going to stack continuously, I think is the right way to go, because otherwise you're going to be saturating and killing lots of area. And so you might want to work that out, but there's a trade-off. The more red you go, the more red stars, okay, are causing that. And you see through the galaxy better, okay. There's less in the blue, but you're not going to make it through as much. So you should work out that for different depths and just sort of see what's optimal.
I think that makes a lot of sense. We were hearing yesterday from Eric that maybe if we tried doing a ton of 1-second exposures, it might overly stress the computing processing. So there's also other boundary conditions, but that's definitely something to consider.
The camera system more than the computing processing. So there's actually some camera limitations to the sequence, to the short sequences of short observations.
Any more comments on the neutrino case? If not, anybody else wants to report on their findings, the solar system objects? Tim, yep. And yet our schedule is very flexible. Just as a reminder, it is a discussion, a base workshop. We'll try to stay within the time. There.
Hey everyone, it's Tim Lister. So the solar system group, there's only 2 of us actually physically here. We got valuable contributions from one of the people that's working on the link framework. And we had some productive discussions in the meeting here. We also had discussions with some of the folks online via Zoom. The solar system community has generally been working on this separately from the meeting in our own sort of Google Docs and in the main LSST Slack. So we've just been prodding along with that. The main things we're sort of working on is refining and writing down and refining our algorithmic trigger conditions. So these are going to be things that are available in the JPL Scout alert system, which gets sent out when new objects are discovered and are potentially on impact courses. So we're trying to figure out a set of parameters that we can pass to some coder to generate an algorithmic trigger for close approaching asteroids. The other area we're sort of focusing on and developing into a TOO case to bring forward is objects of any sort that are discovered in the near sun twilight region and that we might lose before either the near sun twilight goes back there in roughly 4 days, depending on what the cadence gets decided at, or if those objects are going into like solar elongation or somewhere where we wouldn't be able to recover them and they have enough uncertainty that we would risk not recovering them. So I think that's generally where we're at. We're still plugging along.
Okay, any question to solar system objects? Bob?
Thanks, Tim. Bob Blum. This is maybe a naive question, but it seems to me the solar system case is a bit different than the other 2 cases in the sense that I think you're asking Rubin mostly to find the initial object of interest and then perhaps use Rubin to follow it up later, whereas the other messengers are coming from independent triggers. Is that the right way to think about it?
Yeah, I think that's accurate because, you know, the Rubin's is by far the best discovery machine for these type of objects. So really, I think the line we're sort of trying to walk is, are there cases where it is a Rubin discovery and we are unable to get follow-up on something else like DECAM or Gemini or something else? And so it's, you know, there are other facilities. The uncertainty for us as the solar system is how much time is actually going to be available on those other facilities. So I think one of the things that the way we're sort of trying to write the algorithmic triggers is if the combination of the brightness and the ephemeris uncertainty is growing or is predicted to be such a thing in, let's say, T plus 24 hours, that it's not doable with a 4 meter and DCAM, or it's not doable with a 8 meter and a GMOS type things, which would require Rubin's unique combination of field of view and depth. I think that's the path we're sort of trying to walk down.
Right, and those initial discoveries would come through the Minor Planet Center because they would have the asteroids from Rubin.
Yeah, so the workflow we're envisaging is it will come out of solar system processing, it will go to the Minor Planet Center as it does normally. It'll get picked up by the Scout system at JPL and CNEOs as it does now because those 2 mirror. And then Scout will do the impact probability assessment and send out the alert on, you know, this has the potential to pass within X, where X may be less than 1 Earth radius.
Right. Okay, and I guess there's still the off chance that some other facility will find the initial object and it'll have some large uncertainty in its projected position, and then Rubin would still be possibly the follow-up.
We're thinking about that, is whether we actually need to encode a time since something else observed it, or whether the So Scout does the ephemeris predictions out into the future, and that's obviously based on the distribution of observations it's got so far, including things from things that are not Rubin. And so it's a question of whether that and its predictions is enough to make a decision on whether to trigger Rubin's TOO or not, whether that will capsulate enough of whether it's a Rubin TOO only problem in the future. I see there's a question from, well, there's a hand up from Mansi. I don't know if that's me.
Yes, Mansi, please go ahead.
Hi. So actually, I mean, this is a question for the solar system group, but even maybe that's probably relevant for the other ones as well. So the question is, I mean, basically, can some of this follow-up be done as a sort of tweak to the wide fuzz deep, as opposed to as a additional TOO? For example, to articulate this, I mean, I think the solar system group probably has flexibility on which filter they trigger on, and say it's field A that they want to trigger in any filter, and Rubin is scheduled to do this 2 days later. If the scheduler just bumps it up and it gets done tonight instead of 2 days later and doesn't get repeated then 2 days later, then just this rejiggering of the existing cadence, right? Could that help address some of this, since the discoveries are coming from Rubin? I mean, those fields are in Rubin, and if there's filter flexibility, which I think is the biggest constraint with the deep wide fast survey, is that a possibility? I mean, this also relates to Timo's question on GW. And we've been doing some of this with ZTF, and possibly Eric or Peter, Joachim, or Bob have thoughts on whether this is a direction we should even consider or think about, or is it not something we want to go down?
I'm not going to say much about the GW aspect because I don't know a great deal about that, but for these close approaching NEOs, these are things that would be either passing the Earth or potentially impacting the Earth in less than 3 days before the regular wide fast deep cadence would get back to it. I don't know the details of whether the scheduler could then go modify the revisit time to go cover these fields of interest. That sounds hard and complicated and not something they would want to do, but
it would just be sort of pulling forward that field. So say it's scheduled 3 days later, right? And if the filter is flexible, then it can just get pulled forward in theory. I don't know how difficult this is in practice. So that's the idea.
Yeah, I mean, I in principle, yes. I mean, what you're looking for this is more astrometric measurements to refine the orbit as soon as you can. And that has to be typically within 24 hours. The best ways to go achieve that, whether that's a TOO on a different facility, a TOO on Rubin, or a modification of the cadence, is still TBD.
Yeah, this is Jeff Cookie, and this isn't my area, so sorry if this is naive, but if you're doing these, do these or you might have said this, do these include like twilight observations if they're coming inner Earth direction?
Yes, that's the sort of the other aspect of the sort of the two science cases we're sort of putting forward, is things that are discovered in the twilight case that would be coming towards us. I should have mentioned that and I forgot about it. Yeah, we've got a sort of general category of things found in the near sun twilight region that we are not going to be able to recover, and Earth approaching asteroids coming out of the near sun would be in that category. I think Tony had a hand up.
Yeah, thanks. I think that that's my understanding as well, that improvements of the track linkage, especially for PHAs, will be 30 degrees altitude, and there's not very much other LSST observing, particularly wide fast deep, at such low altitude angles. I think Peter Joachim probably has some comments. We'll have some comments on this.
Yeah, and maybe it's a nice transition. If there are no more questions about the SSO case, maybe we transition to Peter's talk actually. So thank you for all the reports back. Thank you.
Wow, did you reformat it even? I mean, did you put it in the template or did it just swallow it? Oh, okay. Yeah, cool. I was gonna be really impressed. Okay. Hi, everyone. I'm Peter Yoakum from the University of Washington. I'm writing the scheduler code, and we also run lots and lots of simulations with for the full 10-year survey. And so I'm going to talk about a lot of the simulations we've done inserting TOO interruptions and following them up and how that's worked so far. All right. Very brief introduction to the scheduler. Here is the survey footprint with all the different regions marked off. So the big green region, of course, is your favorite, wide, fast, deep. We have deep drilling fields, north ecliptic spur, galactic plane, all that good stuff. Yeah. Oh, cool. Good idea. Awesome. Very impressive. Okay. So the scheduler, very briefly, it's just a decision tree that marches down. So at the top of the decision tree are the deep drilling fields. We pre-script those. We just write out when we want them to be done, about 100,000 observations. We just say what times those should be executed. So that's about 6% of the total time. We try to sample. Oh, yeah. Got you for the screen sharing. Okay, and then slideshow. All right. We try to take long gaps where we image a part of the sky, gather a pair, and then image it again kind of 3 to 5 hours later. And so that's only about 4% of the time. Will we do that only on a few nights? The main engine of the survey is taking observations in different filters separated by about 33 minutes. And so 73% of our visits are just this rastering the sky, a big blob of sky in one filter, swapping filters, rastering it again, and then picking a new blob and doing that. If we don't have enough time to do 33 minutes, say twilight is coming up, then we cut it down to 15 minutes. That's another 10%. And then 1.5% of our time is doing these in twilight time, going to very high air mass and looking near the sun to find those interior to Earth solar system objects. And then at the bottom that you can't see is just a greedy algorithm that will pick observations one at a time, so that if we don't have time for anything else, we'll just keep observing wherever we happen to be pointing. Maybe. I don't know how to. Oh.
So we're gonna.
Oh. Sorry. Awesome. Okay, so the DDFs are pre-scripted. Everything else is dynamically generated on the fly. So this is a decision on the fly. So a scheduler is kind of a misnomer. This is more an artificial intelligence that's deciding things in real time. What we want to put in is a new block at the top for TOOs, a block that simply a TOO alert comes in. It generates a new script of observations to execute, and then it just sits at the top of this decision tree to run through there. Okay, so here's what we like to do after our simulations is plot up all our different science metrics on a radar plot. And so this is kind of the results from earlier simulations where we injected kind of 5 to 100 TO events per year, and then tried to follow them up 1, 2 to 4 hours afterwards in just G and Z filters. And it was 130 square degrees per search. And we only tried to follow them up if they were in the regular Rubin footprint. And so on these radar plots, we have lots of different things. We've got a group of solar system objects. So we can say, how well do we recover different solar system objects? We can say, do we make sure we still have templates in the first year? We've got supernova down at the bottom. We've got brown dwarf volume, X-ray binaries, all kinds of fun stuff on here. Sorry, these plots are confusing. Blame COVID, because I was trying to work from home and trying to visualize these, and my kids kept coming up and saying, look at the stats on this Pokemon I just caught. And I was like, not now. I'm trying to figure out how to visualize multiple things on independent axes. And so this is where the radar plots came from. Okay. So our new TOO simulations, the latest versions, we vary the number of TOOs per year, 8, 16, 32, 64. The events are uniformly distributed on the sky. So a lot of them, kind of half off the bat are not visible because they're in the north or behind the sun. We vary the number of filters we use. So up to the full amount. And we also do some deep versions where we'll do 4 visits initially, vary the amount of size, follow up 1, 2, and 4 hours after the trigger. And then a second night going deeper in just G and Z, and a possible third night going deeper in G and Z.
So at the first step, when you decide whether something is observable or not, at the moment, are you just taking the location of the trigger, like the center of the map, and if that's observable, you follow it, and otherwise you don't, or do you follow partial maps?
We'll follow it if the footprint goes, as long as the center of the footprint is in the footprint.
As long as the center of the footprint is in the footprint. Okay.
Yeah, center of the targeted, yeah. And we interrupt most of the follow-ups because we're assuming that a lot of the alerts will get modified and we'll say, oh, we don't actually want to follow this up. So a lot of these get skewed. So here's what it looks like on the sky. Here's the number of visits that were dedicated for TOOs. And this is for one of the simulations where we do 64 events per year. Many are outside the footprint, but these are the ones that actually fill in. And for the simulation, we're doing all the available filters are followed up on the first day. And so you can kind of see the stats down there. We generated 640, so 64 for 10 years. We got 223 of those 640 we started taking observations on, and then it works down to 107 we were taking 2 days later continuously. Yeah.
Sorry. Hi, Rachel Street, Las Cumbres. Quick question about the time distribution of the TOOs, bearing in mind that we expect that a number of these TOOs, if not many of them, will come from gravitational wave or alerts, which obviously are concentrated in time between the 05 run mostly. I think I understand what you're trying to do with these simulations, but is there a simulation suite that does that concentration in time?
Wait 15 slides.
Oh, sorry.
An excellent question. We'll get there. Okay, so for just this simulation, let me show the science impact here. The moral of the story, in blue, we've got our baseline. In orangish yellow is the new one. And this is plus or minus 10%. So it's kind of hard to put lots of different science metrics on the same plot. We have to normalize them because, how do you compare your proper motion precision to the number of supernovae? So you can see supernovae take about a 4 or 5% hit. Some of the kilonova models, those kilonova metrics are measuring, can we detect kilonova without an alert if we just happen to catch one blind? And so those are very noisy because they tend to be 1%. And so those are changes of 1% to 1.1%. So you can kind of ignore the kilonova. They're pretty noisy. The supernovae takes a hit. And so that turns out to be the main result of these TOO simulations, is that you're trading off type 1A supernovae for your shorter time domain.
Peter,
yeah,
can you emphasize which strategy are you showing right now so that people don't get too nervous about the current impact of the simulations?
Right. So this is if we do 64 events per year for all the filters on 3 days. So this is a pretty big follow-up campaign. All right, and here's just the impact on depths. And so you take a 0.04 mag hit in your final co-added depth in G-band, and that's just because these follow-ups are so naive. We're now taking G-band observations in bright time. We're pushing G-band to high air mass, and so that's where the main hit comes. And some of the other filters get pushed to higher air mass as well, but it's a really small impact on your final depths, even though we're chasing so many TOOs. And just for the comparison, sorry, I didn't bother setting it to the same color bar, but here's co-added depth in G in our baseline, and after we do 640 TOOs, and because the color bar, but you don't see a huge difference is the point. This is a pretty small impact on this. And so here's a whole suite of TOO simulations where now we're going down to only 32 events per year. And again, you can see the main point is the supernova can vary by you lose a few percent of your type 1A supernovae, and everything else is pretty much in the noise. The Trojan asteroids vary a lot just because those are concentrated in space. And so if we have a TOO that happens to go off in the Trojan cloud, you happen to get lucky and get a bunch. So that's why that's bumping around.
Peter, quick question. When you say we lose a few percent of type 1A supernova, what specifically are we losing?
You're going from something like 150,000 type 1A supernovae with good light curves to your redshift completeness limit down to 146,000 supernovae to your redshift limit.
And this is Federica. This is the Wi-Fi deep supernova. So these are the low redshift sample of LSST supernova, not the high redshift sample. Right. So that's still high redshift, and you might know that number better than I do, but this is not a very deep redshift sample, which we get in the deep drilling fields, was my point. Half.
Yeah, it's something like 0.5 to 0.7 is the redshift limit, I think, on this. I think it's 0.5 for wide, fast, deep, and 0.7 for the deep DDFs. Yeah. All right. Other question. Yeah.
So Peter, you said you stopped your follow-up when the alert is updated. What exactly goes into updating an alert in this simulation?
Absolutely nothing. We pretended it got interrupted. It is not sophisticated yet. Yeah.
It's a probabilistic, a probabilistic function that over time increases the probability that the update causes that overwriting.
Or was it?
Peter Nugent, Berkeley. You randomly dropped these 64 anywhere on the sky, so some weren't observable, so you threw those out. What about ones that were dead center behind the Milky Way? You bagged those as well?
Yep, we went for them. So if I get so
it's not going to be quite this, because we're not going to go after something at a gigaparsec with 20 magnitudes of extinction.
Yeah.
So
and this is doing silly things like, and some of them are in the North Ecliptic Spur where we don't have U-band coverage, so it would be silly to take U-bands where we don't have templates. So yes, you can do lots of things to make this follow-up smarter. This is the initial thing. Yeah.
Hi, Ryan Foley. Maybe this is for the next talk, but did you consider TOOs interrupting other TOOs?
No, it's it might have been sorry. So right now, when we have scripted observations like the DDFs, they'll just execute in order. Every scripted observation has an expiration date, and so it'll go through the first one, and if the other one hasn't expired yet, it'll move on to that one.
Has anybody thought about that operationally?
Probably not. But the algorithm will,
we do end up with an algorithm that has a priority score for TOs. If a TO comes in and has a higher priority score, it will interrupt wide, fast, deep or an existing TO program. I don't think it's difficult to implement. But just a reminder, these simulations are mostly done so that we can see the impact of a breadth-strokes observing strategy on other science cases.
Yeah, but I hope one of the metrics is also the TOO, science.
Yes.
And maybe there's something to be said about this algorithm where this score should include it's already been triggered, right? So in some sense, like getting a second observation or something like that, if you're already started, that should elevate that particular trigger.
Yeah.
Peter, last time we chatted, you were simulating all the KN with really just a GW170817 template. Is that still the case? Because this is, of course, quite a diversity of GW events itself. Another way of asking this is, at some point, are you going to show us light curves with these TO strategies to make sure that we can actually get science out of them?
We'll get there, yes. So I think we have both the classic TOO light curve and a suite of ones, and so you can set it to be like only do the classic or draw a random one from the full library. Here's just an example of how in the baseline versus the TOOs, how the alt-as distribution is different. So yes, indeed, we are pushing to high air mass. And as we were just talking about, how well do we recover these TOOs? And so we've collected a lot of criteria for potential detection and classification of TOOs over the years. We have some from Fed students, we have some from other folks. And so here we just loop over each TOO and say, did it pass our criteria? And we can say, you know, what fraction of the TOs that we did observe did pass this criteria. It would be good to, especially for this group, to discuss what should that criteria be, because I've been hearing different things. I've been hearing plastics say, we just need a color and a change, that'll do it. Tony's online saying we need lots and lots because there are going to be so many other things. So, you know, if you can classify it with 95% probability, that's not enough, because with 10,000 other background sources, 5% of 10,000 means we haven't found the actual TOO yet. So we should refine this so that we have a good criteria that everyone agrees on, that yes, we can identify the TOO event and we can reject all the contaminants that are in there as well. And here's the plot of you know, the mean number of TOO visits per simulation and the fraction of TOOs that pass the detection criteria that we have right now. And so you know, if we do 2-day follow-up, they're all down here, kind of 54 to 60%, and then up here we start getting, you know, 60 to 68% of the TOOs that we've injected and observed are past the detection criteria. And, you know, and some of this is, again, because we're not doing a super sophisticated thing. Sometimes we'll chase TOOs that are dust extincted, or we know ahead of time, we should know ahead of time that we can't get the full suite of observations, but we try to chase them anyway. Yeah.
You're saying detection criteria, but is this actually a classification criteria? So
classification criteria, thank you. Yes, I constantly mix up identification and classification. This is classification criteria. So here's the trends for lots and lots of simulations. As we increase, you can see we're color coded by the number of TOOs we're injecting per year. The dashed line is kind of that 3% threshold that the SCOC has set that they don't want to go beyond. And you can see it really is just a linear trend. And here's that number of supernovae below our redshift limit. And we just linearly decrease as we increase the number of TOO visits that we take away. And our G-band depth slowly gets fainter. And so this is the main trade-off that the SCOC is going to have to consider, is how many supernovae are worth a TOO follow-up.
Just a quick question on the G-band depth. You mentioned, maybe I misunderstood earlier, but I heard a slightly alarming 0.4 megs reduction in depth, and when I see this plot, it's much less than 0.4 megs.
0.04.
Oh, I missed a 0.
Sorry, yes.
Awesome. Okay, I'm worried then.
Yes. 4% drop in final G-band depth. Yeah. An important 0. Okay, and now we get to what happens if we compact all the TOO observations and alerts into just, say, 2 years. So yesterday Fed said, let's compact it. So I ran it last night, and because I have a nice M2 laptop, it ran. So here's the impact for our usual 64 events per year. Here's 64 events per year packed into just 2 seasons. And you can see it's actually, the supernova impact is actually less. Basically, we just wipe out all the supernovae in those, and the other years don't have an impact. So so 05 is actually good. Like if you wait for 05 and just do all the alerts, then that seems to be even better for us and less of a trade-off. And you know, the only other feature you might notice is some X-ray binaries went up, so we accidentally chased some TOOs into the galactic plane and got X-ray binaries that we shouldn't have. But yeah.
Hi, Peter. This is Adam Miller. So you've mentioned supernovae and you've mentioned kilonovae, but there's a third spoke that seems to routinely be a little bit less in the TOO models. And I can't read the labels because they're overlapping.
At the bottom?
To the right. Well, nope.
These are both kilonovaes. These are two different. Those are 2 different kilonova criteria.
Okay, great. Thank you.
Yeah, and yeah, those are both around 1%, and so 1% to 1.01% seems big on this plot. Okay, so very briefly, also I looked at solar system TOOs. So this is the alt-as distribution of pointings where we're looking for Earth interior objects. So in morning and evening twilight, we're tipping way over, rest around, taking observations in quads so that we can get those moving objects. So we're already taking 62,000 15-second visits in twilight, and that runs every 4 days. And so I said, well, let's pretend we find interesting things, have to chase them in twilight the next day. We'll do that by running this every 3 days instead of every 4 days. And yeah, there's hardly any impact. As you can see, You actually, X-ray binaries like it because every now and then you do this over the galactic plane. The kilonova are noisy, don't leave the spike up. And Vatiras, those are the Earth interior objects, so those do in fact do better. So, and our co-added depths, are changing on order of 1%. So this is pretty much in the noise. We can chase twilight solar system objects for almost no cost. There's the conclusions. I think I've said them plenty of times. So we need two pieces of code. We need something that takes a TO alert and generates a script of Rubin observations. I have this rough stand-in now, but as everyone has noticed, it's doing some things that are silly. And we also need to finalize, given a completed set of observations and this light curve, does everyone agree that we can identify and classify the TOO event and any contaminants and other transients nearby? And so we also have some initial stand-ins for those, but it would be good to converge. All right, thanks.
Hey, this is Chef Cookie. Just really simple and really quick. If you go back to where you crunched it into, I think 2 seasons or something. Yeah, right, right there. The kilonova, what's the green one? It just doesn't show anything for the kilonova there. Is it?
On the right here. That's because I ran it last night. Usually I inject 500,000 kilonova. I didn't have enough time to do that, so it didn't do the full Monte Carlo. Yes, that's missing data that is not there because it wasn't run.
Peter, Bob Blum, just for my own edification, when you inject the TOO at the top of the observing stack, how long does it take to recompute everything? Is it essentially instantaneously?
Yeah, because we don't have a full script. We don't know what we're doing 2 days from now. Since that's all generated on the fly, there's nothing to shift around. We don't have an optimization step, which is scary, but also fast.
I just wrap a quick question. So how fast can we get on target from the time that we send in the trigger? How fast can we be on target?
With the current system, we would need someone at the telescope to say, interrupt what we're doing and start the TOO, because we could be in the middle, because our main workhorses are these 33-minute blocks. So if we just started a blob, if we don't tell the scheduler to stop that, it'll be about an hour until we get to TOO. But if someone's there and says, "Oh, an interesting TOO came in," flush the queue, compute where we should go. So yeah, it all depends on the person with the button.
This is Adam Miller. So one of the points that's come up, and I think you even responded on Slack, but people have been asking about what about slightly changing priorities within wide, fast, deep, if say there's a large area and maybe not quite as compelling a case to immediately slew. Is that something that's ever been run? And if not, would it be something possible for you to simulate?
Yeah, so that's so let me go back all the way back. So basically, what we've been doing before is injecting, saying, well, there's a very exciting TOO, we need to follow it up. Let's generate a script of observations and run it. These lower parts where we are observing wide, fast, deep, we're using a Markov decision process where we weigh how long does it take to slew there, what's the current weather conditions in that part of the sky, how much of the survey have we completed there, and we can add a new function in there that is, how interesting would it be for a TOO there, and just put some weight on that. So if all else is equal, we'll go to the part of the sky where there's a TOO. But if the TOO is way over at high air mass, we'll be like, nah, it's not worth going there. So we have a framework where we could totally fold that in. If we get into the regime where we're pumping out 20 TOO alerts per night and we're like, oh, we don't know which ones to do, we can just put all those bananas on the sky, give those some weight. And so we'll cover those more than we would normally. Yes, we can do that.
Do we have any questions online?
Yeah.
I want to cognizant of the fact that Europeans need to go for dinner.
Yeah.
Hello?
Go ahead.
Hello.
Tony.
Yeah, hi.
Yep.
So Peter, it seems to me that what we really require for TOOs is a very secure candidate identification. And you alluded to it before, but as I understand it in your simulations, you have not repeated the observations in whatever filters you're using multiple times in order to retire bogus candidates. And so that, you probably want to repeat it quite a few times every time you observe. I'm just wondering if you have any thoughts on how that would how that would impact your results, or do you actually do that?
We do that. We're doing it at 1, 2, 4, and 24 hours after the alert in some set of filters. Sometimes it's just G and Z, sometimes it's GRIZ, sometimes it's the full 5 that are loaded. So yeah, we're doing that.
So every time so T0, you do it for that as well. In other words, every time you observe, you do it multiple times right away.
Not well, we will raster the full area in a filter, swap filters, raster the full area, swap filters, raster the full area. Right. So we're not going to get instantaneous colors because the 2-minute filter change time is tough, but we are getting, multiple filters at multiple time steps per alert. Yeah.
I think the answer is exactly what you said, but let me paraphrase it. We do a set of filters on every pass, every time we observe, and sometimes it's a more ambitious set of filter. All of the filters that are on the filter wheel. In some strategies, we only have 2 or 3 filters. Those are a little bit more conservative of how we use the TO time, maybe enable more triggers versus a larger set of observations. And we have some metric that quantify our ability to classify, and we can certainly improve on those metrics and then eventually decide what's the best approach here.
Right. Yeah.
Hi, Peter. This is Simran. I have a question regarding the footprint that we have for the event. Can we provide the simulations, a set of observations as a part of the sky map and make it follow those pointings in a certain order if we want to?
You could. We have a default traveling salesman problem that does that. So you can give it an area and it will convert that area to pointings and then order those pointings in a somewhat reasonable way.
So we could, if I may, load like a sequence of observations and ask the scheduler to do it exactly like that. We don't think it's a really good, I think most of the observatory people will tell you, we don't think it's a really good idea because we might have a better way to achieve a certain depth on a certain area in a more efficient way from internally how we design it at the observatory than a sequence that somebody uploads that is less familiar with how the observatory works. So ideally, we will want to know how deep you want to go with some constraint on time intervals between observations and let us design what is the best way to get there.
Hey, Peter, I missed a trick here. So you have a KN classification criteria. Are you keeping track of on which one of the simulated observations you meet that criteria per object? Because you don't have to raster over the full area anymore the minute you satisfy that criteria. Yes.
Right. Yeah. I'm not tracking it at real time as it goes, and I'm also not tracking which of these we've said okay the alert changed, we're dropping it. So this recovery.
Yeah. So that might be worth doing because if we're not covering the full area anymore, once a thing has met the criteria, then you could also potentially put the other observations on the same kilonova over and over again to get higher cadence, or just do the regular wide fast deep survey, which you might want to still cover the full area for uniformity, but you don't have to do it at this time.
Yeah. There are lots of ways. Again, mostly these simulations are how does it impact the other science, and we can move the TOO observations around a lot. We're just getting how many TOO visits can we afford?
Hi, Brent Smith. Just a quick comment from the very deep TO point of view on the ordering of the pointings. So I think it would be, I don't know if this contradicts what was said earlier, for example, by Fed, but in the scenario where we're wanting to go very deep, it would be desirable to go to partial depth across the full, say, 5 pointings, rather than invest in go to full depth from one pointing and then the weather crops out. So if there was flexibility to go to partial depth or the full patch and then repeat and then repeat, that would be helpful. I'm not sure if that contradicts the point earlier about the order of the pointings.
I think that's a good question of how we do. I'd have to, I don't think we sit and stare 4 times. I think we'll cover the area and, loop over that multiple times and then switch filters and do it multiple times. So I think we're close to what you want.
Thanks, Peter. Bob again. It just in that bottom left corner, so this simulation was 5.5% of all visits in the.
Yes.
Okay, thanks.
Okay, in the interest of time, and specifically for those on the other side of the ocean, I would say let's thank our speakers of the session.